Okay, so in this problem we have a 2.5 kilogram textbook, and it's forced against one end of a horizontal spring that has negligible mass, and it's fixed at the other end and has a force constant of 250 Newton meters. The spring is compressed at a distance of 0.25 meters. When released, the textbook slides on a horizontal tabletop with a coefficient of kinetic friction, mu sub k, is equal to 0.3. Use the work energy theorem provided to find out how far the textbook moves from its initial position. Okay, so we have this textbook right here. This is its mass, and it's pushing in on the spring this much. So the spring is compressed 0.25 meters, or 0.25 meters. Now, and the spring, like how stiff this spring is, this is how stiff it is. 250 Newton meters. That's the constant of this spring, like how stiff it is. And so the spring is compressed this much. It's compressed in from its normal place, 0.25 meters. Now what's going to happen is it's compressed in, we're going to let it go, and the spring is going to push, right, really quickly. It's going to push the book this way, and then the book is going to start accelerating, or it's going to have an acceleration. And it's going to start going in this direction, and then it's going to keep going. Well, it's initially going to accelerate. The spring is going to cause an initial acceleration, but once it leaves, it's not going to accelerate anymore. There's no continuous force on it. So remember, F equals ma. So you have to have a force to have acceleration. So initially there is a force that will cause an initial acceleration, but once the thing starts going, there's nothing else there's no additional force that's going to continue to push this thing forward. Okay, so all it has then left is just velocity. So yes, it has an initial acceleration, but then everything else after that is just velocity. So it's going to have a velocity, right? But it's going to get slower and slower and slower and slower. Why? Because there's friction on this table. So there's a table. This is the table, and so it's gonna accelerate initially, and then no acceleration, but then it'll have a high velocity or some velocity, and then the velocity go lower, 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 and then finally it'll stop. So the question is basically, how long is it going to take? What's the distance here for this textbook to stop? Okay, this distance here. Once it's released from the spring. Okay, so what we can do is, maybe we could do some graphs. So a good one that we could do is we could do a force versus x or displacement. Okay, where 0 here, 0 meters, means where the book is right now, in its compressed state. So 0 here means the book in its compressed state, like right before we release it. Okay, so you could do, if you wanted to, you could say, like right here, this is 0 meters. And then here, this is where it's going to stop. We'll call this, X or whatever. Well, maybe not call it X, but like call it S for stop. And so what we want to know is what's the difference between this point here and this point here? How far did it go once it was released? So the force here, down here. So this is actually what we're looking at is the spring. So the spring graph is going to look like this. Okay, let me explain this. So this X means how much is the spring compressed or stretched. Like how much did you compress it in, or how much did you stretch it? So when you first start to, for example, here compress the spring, is it hard to do? No, it's pretty easy, right? It's pretty easy. But as you compress the spring more and more and more and more, there's more force required, right? Because it's getting harder and harder to compress it even more. So therefore, the spring it's getting harder to push because this force is getting stronger, right? And so this slope right here is basically K, okay? Because K is, so this is the force as a function of X is 250, which is what we have here. And it says Newton divided by meters, because this is in newtons and then this is in meters, right? And so therefore the slope is the newtons divided by meters. So, but this is a linear slope, right? So it's 250 x. So that means if I know my x right here, if I know this, I just pop the x in times 250, then you get your force. Now, we happen to know this thing is compressed in 0.25 meters. So we actually know this value is 0.25, okay? So if you say 0.25, which is right here, it goes into this x, times 250, you'll get the force. Remember, because this force as a function of x. So if I pass in the x, I'll get a force out. Okay, so that then, maybe I'll use yellow or something. Okay, so that's this value here. And it's 62.5. Okay, 62.5. 62.5, and this is in newtons, of course. So the spring being compressed in 0.25 meters causes the force that you would feel, or the force the force of the spring would be 62.5 newtons. Okay, great. So then we know that, but we're talking about work and energy and things like that. So how much work do I have in this compressed spring? So meaning when I've pushed the spring in this amount, when I've compressed it in, obviously that's going to require some work, right? Well, how much work is that? Well, remember the force over x, force versus x, it's just the area under the curve, okay? So this, maybe I'll make it green. So this area under here is work. This is the work. Okay, let's just make this here, and we'll say this is work. So all you have to do, how do you find this? Well, it's pretty easy. You just do 62.5, which is this, times 0.25. This is just a square. Well, not a square, but it's a rectangle. You just do this times this. But it's this times this, but it's half. It's half of that, right? So it's half of this times this. And if you do that, you'll end up with 7.81. Equals 7.81 joules. That's how much work you have, maybe using your muscles, you have put into this. So you've taken your muscles, and it has, your muscles have done 7.181 joules of work. And now, guess what? Now the spring now has 7.81 joules of energy, potential, we'll say P for potential energy, because it's stored. So the spring initially the spring had 0 joules of potential energy before you compressed it, right? Before you compressed it, it had no energy. But then once you compressed it, you took the energy from, say, your muscles, and now that energy has been transferred into the spring. So the spring had 0 joules, now it has 7.81 joules, okay? And now we're going to release it, right? We're going to release the energy. We're going to release the spring. So if we release the spring, then that means the spring is going to go back to no energy. So it's going to go back to 0 joules of potential energy, okay, the spring. But when we do that, when we release it, that energy, where did that energy go? Well, it got transferred into the book. So remember, when you talk about work is just a thing that transfers energy from one place to another place. So now, the book, let's call this book, it now took the spring's energy. So now the book now has 7.81 joules. Now it's not potential energy, because potential energy is like stored energy. So in this case here, it's kinetic, because the book is moving. So kinetic means energy of motion. Okay, and then potential means it's stored. So we took the energy, quote unquote, from our muscles, put it into the spring. Energy from our muscles, put it into the spring, and then took the energy from the spring and put it into our book. So you could think of our muscles as maybe like chemical energy. So we took chemical energy, stored that, changed that, change it to potential energy, and then change the potential energy into kinetic energy. Great. So now that I have the kinetic energy of this book, we can figure out how fast it's going, right? We can figure out how fast it's going. Now, before we do that, which you could actually do that, you could say, because you may remember here, if I know the kinetic energy of the book, that if I have some energy, kinetic energy is equal to 1/2 mv squared, right? And I know the kinetic energy is 7.81 joules, and I know 1/2 as well, 1/2, and mass is, it told us the mass, 2.5 kilograms. 2.5 kilograms. And then V, of course, is V. This V squared is what we're looking for. Obviously, you can just do the math, half times 2.5, and then say do 7.181 divided by that, and then take V. You obviously you have to take the square root of it, and then once you're done with that algebra, right, you end up with V is equal to 7.07 meters per second. So when the spring launches the book will initially have a velocity of 0 meters per second initially, but then after you release the spring, it'll then go to 7.07 meters per second. So now the book is now traveling at 7.07 meters per second. So that's pretty cool. But now it has a velocity, no acceleration now. Now the thing is anything going to stop it? Is anything going to slow this book down? Yes, there's friction, right? There's friction right here that's going to slow this down. So we're just going to slow the 7.07 meters down slower and slower and slower. Maybe it'll go 7 to 6 to 5 to 4 to 3 to 2 to 1 until finally 0. Okay, so what we're going to do is we're going to drain off. This velocity, of course. So there's a lot of ways of doing this. And so another way of doing this is just saying, of course, there's multiple ways to solve this problem. But if we want to solve this using energy, what we can say is, okay, the book has what? 7.81 joules of energy. What happens when the book has no energy? What's its velocity going to be? Well, 0, right? So if there's no velocity, then there's no energy. So I want to remove all of this energy. Okay? And so how are you going to do that? So let's look at this. So I'm going to draw another graph. Force. Here's the force. Here's X. And so here now we're talking about up here at the top, this one was the spring. So this right here is the spring. The force of the spring. And here what we're talking about is the force of friction. Okay? And so whereas here, if we look at this for a second, you can see that the spring the force changes depending on how much you compress or stretch the spring. But what about friction? As you move along the floor, does the friction change? Does it go up or down? No, it's constant. Whatever the friction is here is the same. So the friction is constant in this case. So we have some constant friction. We don't know what it is. As it's moving along the floor. But at some point here, it's going to stop. Now, do I know where that is? No. So they're here. At some point, it's going to stop, and this is 0. This is the initial. Remember, this is X is in meters. Okay? Remember this is X is in meters. So remember, this book here has 7.81 initially, 7.81 joules of energy. But what if the friction were to consume that energy and then maybe turn it into something else? In this case here, it would turn it into, because what happens to it after the book stops? So the book stops, right, and it has no energy. Where did that energy go? It had to go somewhere. So it actually made the tabletop hotter. So it changed the kinetic energy into thermal energy. So you could say then the book then had 0 kinetic energy, but then let's call it the table, if you will, had 7.81 joules of like thermal energy. right? Because the atoms got hotter, and so they started vibrating. So you went from, like up here, chemical energy, which was my muscles, got turned into spring, turned into the potential energy of the spring, which turned into the kinetic energy of the book, which turned into the thermal energy of the tabletop. So you could see here that work was doing something. It was moving this energy around. Okay, so back to this. So the book initially has 7.81 joules of energy. But what if the friction, which is here, drains all that? So remember, this is the force versus X. So what I'd like to do is I'd like to say, okay, I want to drain 7.81 joules of energy. Well, how am I going to do that? Right? So I want to find out my displacement. How long from zero meters to this? How many meters is it going to take me to drain this much energy? Well, I'm gonna need to know this. Now remember, this is friction, and so you may remember that friction. So if we draw our diagram, our free body diagram right here, this is the book, and so this is mg, or weight. And then this is the normal force, right, which is opposite of that. And then our frictional force is this way, right, friction. Remember friction is mu sub k, kinetic, times the normal. And then normal is just mg. Here it's just mg. So F, the force of friction is actually mu sub k times m times g, okay? And if you do that, you'll get 7.35 newtons. Right, 7.35. So this is 7.35 newtons, okay? So now I know this, and I know this, but I don't know this. So this is just a regular equation, right? All I could say is, if I wanted to, is the area that I'm looking for is 7.81, and that equals 7.35 times, let's call it x, okay? Then all I have to do is divide by 7.35. It gets rid of that one. And then I just have x equals 1.1 meter. And that's it. So what just happened is this friction now, as the book is moving along the table, it's consuming or draining more and more kinetic energy from the book, draining more and more and more and more and more and more and more until finally it stopped. And now there's no more energy to drain, right? It's now drained. It's drained all this. Let's maybe make this like this color, something like this, okay? It's drained all this energy. And how long did that take? Well, not how long, but how much distance did it take? 1.1 meter. Okay, and like I said, there are other ways of solving this, but I just want to solve this using work and energy. So I guess the main point of this is that work is transforming energy from chemical to potential, from potential to kinetic, from kinetic to thermal. Okay, so work is the change agent. It is changing the energy, and the total energy never changes. Right? We had 7.81 in our muscles. It went into the spring, it went into the book, it went into thermal energy. So that 7.81 joules never actually went anywhere. We still had it. The total energy in the system is always the same. It's just work is just moving it around. It's just moving it from here to here to here to here to here. So work is just moving the energy around from place to place to place to place. But the total energy will always be the same. All right, that's it.